I need that there's this guy from UFH who does it.
I see we are live on YouTube, so I shall stop talking. Oh, wait, yeah.
We are indeed. You can carry on your conversation.
We have 2 more minutes. I need to calm my nerves.
Yeah,
okay,
we can't.
I'm letting our speaker have his time to get.
We can't start until past because obviously we're broadcasting. Carry on your conversation.
We have 2 more minutes. Where's Peter?
Peter's going to be joining on YouTube, not on Zoom. Yes. So, Carl, when we hit the 1:30 mark, should I just start by introducing our speaker?
Absolutely, you're the host, the chair. Peter will tell me.
All right. I hope we all practice our thinking faces. I see Trevor and Helen are all ready.
I'm going to let you kick off in a minute, Madam Chair, because I'm going to be just advertising the link to everyone.
Okay, can you just give me a thumbs up when I should start talking, because I'm looking at you now. Good afternoon, everybody, and welcome to FAST. My name is Tiamo Malele. I am one of the hosts for this week's FAST Habitable Planet Workshop, and I will be introducing today's key speaker. Today's key speaker is Ndou Letendou. He is an earth scientist, a geologist by profession, and he works at a coal mining occupation, as an environmental officer. He holds a degree from University of Venda, an honors degree, and he's also a certified natural scientist. Letendou has been with Access for over 3 years now. He's been a planeteer, he's been a core lecturer, he's also been nominated for the NDA award. He's also sat in the National Representing Council as the treasurer. And on one side, he owns his own geo consulting company called Matava Environmental. He's currently reading for his master's in environmental geology. Please help me in welcoming our key speaker for today, Letendou.
Thank you, Tiamo. Thank you, everyone. I'm happy to be here today. This is my first time actually presenting a key lecture, and I'm way excited and nervous at the same time. So I'm just gonna proceed and share my screen. All right, stand up. Everyone can see my screen?
Yes.
Okay. As Siama has said, my name is Ndou Letendou, and I actually studied my honors from first year at the University of Venda. And I'll be taking you through a very complicated talk or key lecture today on geopolymerization of tailings. And this geopolymerization process has always been known as green cement. And you'll actually hear some of the reason why we term it green cement. And that's just the introduction that Siama has said, then I'm gonna skip it. So in this talk, I'm gonna take you through the physicochemical properties of tailings materials, which are our main materials for geopolymerization. I'm also gonna deliberate with you some of the mechanical strength of a fully produced geopolymer. And I'm also gonna characterize a little bit of the geopolymer, looking at the water absorption and its reacted phases when it has reacted to be a fully formed geopolymer. Now, let's start by defining what are tailings. I'm sure to most of you, this is a very new word, but those who are in geology and those in environmental and mining would be familiar with it. So in a mining industry, what happens is when they started stripping, when they started removing, when they started to wanna, let me just give you, I'll always make a reference to coal mining, because I know more of coal minings. So in coal mining, what happens is they're going to strip the top layer that we all see, which is what we call an overburden. So they're going to put it away. Now, as they go close to the coal, they're going to come across what we call shale. It's another type of a rock. Then all those materials that they take through, they're going to pile them. And then when they take the actual coal itself, they're going to wash it. When they wash it, they're going to separate coal from the discards. So those discards also form part of what we call tailings. However, tailings are quite broad. Like what you see here, this picture, I took it in Joburg. These are the tailings in Joburg. These are gold mining tailings from gold fields. So basically what happens is when they were purifying the goods, the material that were left behind, they stockpile them somewhere else. And these materials, they mainly, they will have some constituents or the remains of gold and other elemental materials that are left with or that were found in the rocks. So with close association, you know, gold, you can find it with other elements such as PGC elements, which are the platinums, your copper, all those heavy toxic metals would be found in that association. So these tailings materials, they occupy over 1 billion of spaces of hectares. That means that if they occupy over 1 billion hectares of spaces globally, over 1 billion of hectares, that means there's over 10 billion people who are deprived of a space that they can stay or they can reside because of this tailings material. And also another thing is that these tailing materials, since they contain some of the toxic elements that were there on the ground, when it rains, those toxic metals are mobilized out of the tailings, and then they can actually contaminate the environment. So that's where the cases of AMD comes in, acid mine drainage comes in. And also in turn, these tailings materials, they can react and then form another materials or another contaminations that are just in there. So basically tailings are a nuisance. In as much as they bring the purity or they bring the gold out of it, they're a nuisance. And for some reason, the environmental assessment practitioners, they also do visual impacts when there's a mining. And they say, these things are also not good for your eyes. When you it annoys some of the people when they just actually look at them. So those are tailings material. Now, that's why they are a problem. And when we actually define a geopolymer started resurfacing in 1948 by Joseph David Out. This guy is the one who actually brought through this theory to life. And he defined geopolymer as inorganic, typically ceramic, materials that form long-range covalently bonded, non-crystalline and non-crystalline networks. So let's just actually unpack a little. So when we speak about covalent bonds, you all know covalent bonds are one of the strongest bonds that we have. Non-crystalline, it means they don't crystallize, they're amorphous. It means they're just available everywhere. So they actually create that non-crystalline network. So when we say network, it means amorphous material, they're actually joining each other to create a long range of network. And if we bring in covalent bond in that long range of network, that means we're speaking about a very long, strong, inorganic, covalently bonded network of materials. So how do we then actually create a geopolymer? So we create a geopolymer through a process called geopolymerization. So geopolymerization involves the conversion of aluminosilicate materials or aluminosilicate tailings materials into mechanical stable construction materials. So there are quite a range of polymers if we just look at polymers itself. Civil engineers, they create their own polymers. Chemists, they create their own polymers. So when we speak about geopolymers, there's the word geo to start with. So geo, it's just geological polymers. So which means these polymers are actually from a geological source or from a geological environment, of which in this case, we're going to focus on tailings materials. Now, one can ask, why do we really need to polymerize them? Why are we looking into polymerization of these materials? But the idea is that now we are moving into a green solutions. We're moving into green metals. Everything that we do is green. Some, even when they eat, they will tell you that they need to eat green food because it's more healthy. So green has always been associated with good things. And now they actually introduced the concept of green buildings. So green buildings are buildings that actually have more windows. That is the main definition, that they actually bring in more light and you don't actually need to use the lights that are in the room. But by bringing in more lights, you actually by bringing in more, by having more windows, you're actually eliminating the use of cement. You're actually eliminating the use of also bricks. So that's where the green matter concept comes in. Then the geopolymerization of tailings materials, what we're saying, we actually convert those tailings materials that are there, that are potential environmental problems. We actually convert them into very stable construction materials. Now, this is what we call a green cement. And I'm sure when we speak about cement, most of you are familiar with PPC, which is the Portland porcelain cement, the PPC that we use. And I think it comes in two range, which is 23.7 Newton strength and the 42.7 Newton strength. Now, the geopolymer supersedes the strength of both 42 and 72. So which means this is a more stronger green cement that we have than PPC. You'll actually see the evidence as I bring in the experimental views of it as we're moving forward. Now, part of the reason why I'm saying it's stronger is because of this chemistry that comes in, the covalent bonding of networks, which is not there on calcium cements that we're actually using. So another problem with the calcium cements that we are currently using, number one, they have to be mined. So if they have to be mined, it means there's land degradation involved. And in all cement station, and I think the major producer in Africa is AfriCem and PPC. And I heard now they're about to merge. So which means we're going to have them as the major producer of cements in the whole of Africa, AfriCem and PPC. And PPC is quite dominant in South Africa. So PPC has mines. In those mines, what they do, they actually mine calcite. So they actually crush it to make sure that it becomes in the powder. Obviously, they do add some chemicals, but they also put it through a process called calcinating. So calcinating is basically burning of the calcite material under a kiln. So which means that a kiln is a thermal process actually. So in a thermal process, wherever the thermal process, there are gases that are being released. So that's pollution on its own. And mining of calcium and making it to be that fine powder, it actually produces a very, very disturbing dust. So already we have air pollution being contributed there by PPC. And by average statistics, to produce one bag of cement, just one bag of cement, you're going to have to use over 20 units of electricity. You see the units in your house there, the electricity, if you are using the meter box. 20 units, if the box says 20, you can actually last for a day. But that 20 is being consumed by just one bag of cement. So already these cements, they're actually taking a lot of electricity or a lot of energy. They need a lot of intensive energy to produce. And in turn, they're also producing to pollution in the environment. So that's when this green matter comes about. So this is the guy called Joseph David's house, which is J. David's house. And okay, I was supposed to write 1978 there, my bad. And you can actually see on this picture here, it's actually presenting about geopolymers. So this guy was actually dedicated in this polymerization process. Now, in short, what we are saying with geopolymers. Now, let me shift straight to tailings material. We defined geopolymerization as a process of converting aluminosilicate materials using alkaline solution to produce what we call a geopolymer. So to create this green metal solution or this green cement, what we need to do, we need to have tailings materials. So tailings material, you need to get them everywhere. And you need to have an alkaline solution, of which in this case, on my studies, I actually used sodium hydroxide, but you can use a range of alkaline solutions. Now, when you mix both of them, they form a pulp. A pulp, it's like mud, it's muddy, it's a pulp. So we call that a geopolymeric pulp. And then when you cast them into molds, so molds is just to make sure that they take shape and you put them in an oven. So one part that we did not discuss in the definition of a geopolymer is the part where there's an oven. So at some point, geopolymers needs to be put in a curing temperature. And they actually form at a temperature of about 90 degrees Celsius going upwards. So temperature needs to also be involved there for you to form a geopolymer. So at this stage, we have three parameters or three methods that we need. We need this alkaline solution, we need a sample, which is a tailing in this case, and we also need a temperature or curing temperature or elevated temperatures. Although there are ongoing studies in China, Hong Kong, and Japan. And there are ongoing studies of saying that we can actually produce geopolymers on room temperature. But at this stage, those are ongoing studies, they have not been proven. At this stage, you need to produce it under an elevated temperature. So when you put it under an oven, that's when you need the temperature. And in the oven, that's when you demold for them to actually get that curing temperature nice in the oven. And then you crush them. So crushing is basically a mechanical process, which is a geotechnical technique for you to actually get the strength. That's why in a cement, they actually tell you that this cement, PPC cement, it has a strength of 42.7. It's because they've put it under crushing. You'll actually hear more of this when we go forward. So in short, or in pictorial view, this is what we are saying. You need to have a sample. So these are fly ashes. So fly ash is basically, so what happens in a coal mine, when they mine coal, they take it to the power station for the power station to produce electricity or energy. So the process that is involved there in the power station, it's a thermal. I'm sure if you have passed through a thermal station, you actually see air coming out there. So it's a thermal process. So that thermal process, it burns the coal to energy. But there's also some materials that are left after burning coal. Those materials that are left are called fly ash. So imagine on the power stations that we have in South Africa, how much of the fly ash that they have. Because this is a constant process that is going on of burning coal, so that South Africa can be maintained. So fly ash can also be used. We have melter lean materials. So basically all these are aluminum silicate materials, which I prefer to put them under one class of tailings. Well, lately, the civil engineers, they're also using geopolymers in making what we call cement. You know, cement is actually into concrete. So concrete is actually a combination of cement, water, sand, and aggregates. So those black stones that we actually call concrete, they are not concrete, they are aggregates. So the mixture of all those, it's what forms a mortar. And that mortar is what we call a concrete. So civil engineers as well, they've actually started researching. I've seen a few research from University of Pretoria, the civil department. They're also researching also into using this green cement, into making it, into casting them, into making your slabs, etc., etc. So that's where you see this parts where there's mixed designs with aggregates and cement. So this is from a civil engineering perspective. And also, there are also some who are doing reinforced GPCs. And you can actually see the GBCA, they're actually used, mostly they are used to just strengthen the structures. So in this case, you can see they use sodium silicate as an alkaline solution, and they also put sodium hydroxide there. Both of these are alkaline solution, and they are actually mixed with fly ash. Now, what you see in this picture, I hope you can also see my cursor. What you see in this picture is a picture that has been taken under SEM, scan electronic microscopic. So SEM, it actually takes a very close picture that actually shows you the crystalline structure of a material. And in geology, that's what we call the morphology. So that's what we actually zoom to see. And when you have mixed one of the solution and the fly ash, you have fresh GPC that can be molded and casted, and then you can form a very nice strength for your building. Now, I actually tried to actually broaden this for us to actually understand this. Now, this is a coal-fired power station. So this is where the fly ash comes in. And these are the alkaline solutions, sodium silicate, hydroxide. And this source material, which is from a coal power station, is put under curing temperature. Now, the curing temperature is where you put it on an oven. Then when you put it under an oven, it forms a geopolymer. And after you form the geopolymer, you can cast it anyhow, which means you can actually form bricks. This is already in a slurry form, which means you can use it as, this is in a slurry form. You can actually use it as a cement to build with, and you can actually use it to make bricks. You can actually use it to make any construction material. Now, that's where we come with the green concept. Now, this process of geopolymerization, it does not involve any burning. It does not involve any pollution released into the atmosphere as compared to creating a normal PPC cement that we use. So this is more of a green solution. Although now the challenge with it at this stage is that you need to build a very big fan. a very big oven, I mean to say, where you can actually put this material to chew in. And you need a must produce of sodium hydroxide or alkaline solutions. Well, an added advantage to this one, to this method of creating this cement, is that the source materials are available. I mean, if we have over 1 billion of 1 billion of tailings just packed around the whole country, then which means the source material is available. And it's ongoing, these materials, this source material. Mining is continuing. Or unless, of course, if you stay in countries that are actually burning, like the UKs that do not have any mine at all. So, sorry. So other than that, these other countries that actually develop very well into making sure that we have this very nice cement. And even South Africa, I mean, South Africa, we have over 20 mines. And I guarantee you that in those over 20 mines, we have over 500,000 hectares of tailings that are just packed. Those are active mines. Let's not forget that those mines that have closed, the ones that mines that operate many, many years ago, and they were not rehabilitated. So in an essence, we have a lot of material that can actually contribute to making sure that we have this green matter. And also living greenly, it's also contributed to us reducing less on climate change. So that's why this concept of geopolymerization is important. Now, let me just actually take you into my journey, into my scientific journey of when I created my own geopolymer. So basically what I did, I was using copper tailings in this one. This was also part of the study that I did when I was doing my honors studies. So we dried the sample material overnight, and then we physically, chemically, and geochemically characterize the geopolymer, just to know what is in the geopolymer, what actually controls the geopolymer, what is in the material, I mean, what is in the tailing material. So this is the characterization of the tailing material. To actually understand the characteristics of the tailings material, so then we can know what actually controls the end product of a geopolymer that we use. Let me take you through the journey. So the research questions that I had were as follows: what are the physiochemical properties of the tailings, the strength of the geopolymer, how does the geopolymer react with water? And you must understand why of all properties did I decide to choose water with a geopolymer, because water actually weakens the buildings. If your house gets a lot of rain, you'd actually at some point it will actually collapse or slide. So water is actually a main factor in construction strength or into mechanical strength. And lastly, I looked at the phases of a geopolymer to see that amorphous covalently bonded reaction. Now, this was actually my research methodology, and I actually use 5 concentration moles of sodium hydroxide, 5, 10, and 15, to actually see how do the concentration of sodium hydroxide affect the strength. And I kept the temperature constant at 90 degrees Celsius. It was not there are also other studies that actually investigated the effects of temperature that kept the mole ratio constant. But for me, that was not really of interest at this stage. So I sampled the material. Basically, this is just your normal, if you're doing your honors or you're about to do your dissertation, this is how actually you need to actually pictorially or graphically represent your methodology. So what I did actually, I sampled my material, sampling them, I dried them overnight, which formed part of the sample preparation. And then I characterized my materials, which are my tailings, through physical properties. I did civil analysis, moisture content, and I did specific gravity. You must understand that all these are geotechnical properties. Hence, we are looking at a geopolymer. And then chemically, I did the pH. Part of the reason why I did the pH was to investigate to see what is the pH before and after. Is it acidic before on the tailings material, and after, has it changed after being on the tailings material, and after it has been geopolymerized, has it changed? And I also did electron conductivity. Electron conductivity is just to check the metals that are in there. And to determine the elemental composition of the tailings, I used a method called X-ray fluorescence, which is XRF. And because XRF is a burning method, actually. It passes through light, and is a very sensitive one. And it actually bans the organic materials in a sample. Then the XRF does not account for organic material. Hence, I did LOI, which is loss of ignition, to actually determine the amount of organic matters that were lost. And I did XRD, which is X-ray diffraction. XRD is to actually determine the elemental composition. And I did scanning electron microscopy coupled with EDS. So that is just to see the faces. And lastly, I did thin section. So thin section is just to see the minerals that and the minerals that are there in the tailings materials, just using a microscope. Then after that, I geopolymerize my tailings. Then after geopolymerizing my tailings, what I did was to characterize the geopolymer now, to actually compare the before and the after. And number one, I did the UCS, which is determining the strength. Hence, I'm saying I'm confident that the geopolymers have more strength than the PPC cement. And I did water absorption just to actually see its reaction to the water, and obviously analysis. And then that's when I was concluding my studies. And physical properties, sieve analysis. This is actually how sieve analysis is used. You dry your material, you put them under a mechanical sieve, you shake them, and then you weigh before and after. And this is the graph, the gradation curve. And my material was actually composed of 97% of sand. Now, if actually just by stage one of me characterizing, already I could predict that my material is composed of silicate material, because most of the sand grains material are quartz, and quartz is SiO2, which actually forms the broader umbrella of silica. And another properties was moisture content, just to determine the amount of moisture that is there on the soil, on the tailings material. Then I just took wet samples, weighed it in a balance scale, then put it in the oven. Then after that, weigh again the dry sample from the oven, then dry it at room temperature and then incubator, so that no other moisture is lost. And I was able to come up with my moisture content. And what I actually found out is that my water was between 13 and 30%, and about 0.13 and 0.3. So that was like quite a very low moisture content that is in there. So those are just actually the wet mess that I did. I got 30 grams, and the dry mess was 30.09. Then you subtract both of them. After subtracting both of them, you multiply by 100, then that's when you can get the 0.3%. So another property which was of interest was specific gravity. The specific gravity actually plays a big role in rocks, or in tailings material, or in geological materials, because they actually tell you how those materials would react in terms of the strength. If you have high specific gravity, that will actually tell you that these materials are going to have high strength, and vice versa. And I think specific gravity can more or less be related to the density. And I think you guys earlier on had a discussion about the density of the oceanic crust and the earth crust. And you actually found out that I think the earth crust, which is mostly composed, the oceanic crust, which is mostly composed by basaltic rocks, had actually low density than the earth crust. That's why we have volcanic reaction, because the other one submerges on the other because of the density. I'm sure you have a wonderful discussion on that topic for another day. So this was my specific gravity, which was 2.8. And the benchmark for strength, geotechnically, when you are characterizing, if you have a specific gravity of over 1.5, that means your material is very strong. And obviously, it should be strong if we have quartz. I mean, quartz is one of the minerals that are resistant to weathering. That means that actually proves that they are actually strong. And chemical properties, I did pH and electron conductivity. I did pH for 28 days, just to actually, the water was submerged into water for 28 days, and I measured pH for day 1, day 2, day 4, up until day 7, and I skipped a few other days, went to day 14 and day 28. And you can actually see that these tailings materials were alkaline. So that was an advantage already. And the conductivity of the material was above 400. So that actually tells me that there are metals, other metals, or other toxic metals or heavy metals in this material. So hence, we had to go for XRF and XRD. So this is basically the graph showing the pH versus days, which is what I showed you in the table. And this is basically the conductivity and you can actually see the relationship between conductivity and days. You can actually check on earlier days on day 1. You can actually see that, okay, on my x-axis I have pH and I have days on my xy. I have days on my x-axis and pH on my y-axis. So, but actually you can see that as days go by, the pH started at about 8.8, but it increased, and after that it went down. It's because maybe it was in water, and that's when the water was starting to get more into the materials, and it was under a mechanical shaker just to make sure that I have a good representative. And you can actually see the relationship of conductivity. It almost remained constant, but you can actually see the increasing trend, but on both samples. So basically, these were 2 samples, one is P1 and one is P2, because I was actually doing I actually took 2 samples from the tailings material. And part of the reason why I took 2 samples is so that I can be able to have comparative rather than just having 1 sample. Now, with elements, as I indicated, I used XRF. And with XRF, what we actually did was, this is just basically the method. You mix your tailings powder with boric acid. Boric acid actually forms it's a binder, actually. It binds your pellets, as you can see, so that they can actually be put inside an XRF machine. And inside the XRF machine, this is where you're gonna get your results. And here are my results. And I highlighted silicate and aluminosilicates. And I highlighted silicates and aluminum oxides, so that you can actually see that these materials were purely or had more content of aluminum silicates when they are combined together. And that gives us an over 80% of aluminum silicates. But also, I had to actually look at the elements that were there. And we had high concentration of copper, which is in ppm, and it was over 800 on both samples. You can see this one was 813, and this one was 1,258.1. So part of the reason why copper is higher is because these tailings were taken in a copper mine. So obviously there used to be a residue, but you can actually see a range of other metals such as zinc, arsenic, and lead. And these are toxic materials that should not be in the environment. Mineralogically, you can actually see these materials had over 33% of quartz on sample 1 and over 65% of quartz on sample 2. And you can actually see some of the elements such as epidote that has aluminum on them. They actually had high concentration, which is actually 26% and 11% on the other sample. So basically, this is just a graph showing you the composition of the minerals that were there on my sample for both sample A and sample B. Now, this is what I saw through a microscope, which is doing polysynthesis. So basically, I was confirming this XRD with microscopes, whether I would still see the very same elements that are there. I would still see quartz, I would still see chloride, I would still see epidotes under a microscope. And yes, I did saw them, but obviously, this leaves you to have a lot of training, geological training, for you to be able to identify. You look at the shape, you look at the culture, you look at the shape, you look at the culture, you look at the morphology, you look at the crystallines, you look at the grain size, a range of other properties for you to be able to tell that this is quartz. So this, I would just leave it as it is. But yeah, I was able to actually confirm what XRD did brought through. So I also went through SEM. So SEM, basically what it does, it actually looks at the crystalline structure of the material. And as you can see in this material, if you look at this side, you can see that this material are actually not bonded, they're separate materials. They are amorphous, so to say, in a chemistry way. And you can actually see on, I want you to keep this in mind, the 1 and 2. So this one was taken under 10 micrometers and this one was taken under 100 micrometers. So that is the zoom for you to be able to see. So this is one was actually near and this one was actually a bit inside and far. And you can actually see the single grains as they are divided. But 1 and 2 as highlighted, they actually show you that there is a bit of reaction, but it's not strong, it's not strong. And this is because these are tailings material. These are just earth materials that were just dark there were no any reactions that happened. But I think 1 and 2, the liquor reaction would have been because of they stayed there for a very long time, and they reacted with water, oxygen, etc. Now, after characterizing, that was just characterizing the tailings, then I had to geopolymerize. Now, let me actually put you through these 2 pictures. Picture A, picture B. Now, where you see 1 and 2, this is where you see also on 100 micrometers and on 20 micrometers. So picture A, you can actually see that it's no longer the same as picture A. Okay, I forgot to put picture A on this one. You can actually see that here they are not bonded, but actually when you come here, they're like one material. So that is after geopolymerization. So now you can actually see that network of connection of material that are covalently bonded. And zooming a little bit, you can actually see here, this is 2, which is this 2 here. Oh, this is 1 actually, sorry. This one that you see here is this one that is here. Now, you can actually see that this material, they are almost not distinguishable. You cannot actually distinguish a single grain. They're actually covalently bonded. And these are still the tailings materials. So you can actually see that they are bonded on this stage. And that is what we call a geopolymer now. Now, with this bond, the chemistry bond, that's where the mechanical properties comes in. If a material is strongly bonded and it's not easy to break through, that means that material has high strength. And hence, this geopolymer technique can actually be used to bring about this green cement, because they're actually strong and they're actually covalently bonded. Unfortunately, I did not get an opportunity to actually do the same characterization on a Portland cement, on a PPC cement. Actually, I would love to, so that I can actually show you the difference of the bonding of these 2 materials. Now, this is the unigel compression strength, and you can actually see that the highest that we got was 30 UCS for 10 moles, and which is in orange, and for 12 moles in orange. But I want to remind you that this strength is in kilopascals. So if you convert Newton to kilopascals, let's just say 47.2 PPC cement, you convert it to kilopascals, you'd actually get about 5 and 10. So which means the geopolymers are actually 3 times stronger than the normal PPC Portland cement. So hence this material can be used and can be used as a replace for an ordinary cement that we're actually using. Now, I actually put it under water absorption just to actually see what happens if you build with geopolymers. What would happen would if it rains for like 10 days, what would happen? Wouldn't that building just melt because it has more water? And what we actually found out in this study is that day 1, I actually found a very low water absorption percentage, which was about 3%. And when we go to day 4, it increased. And that was a concern for me at about day 4 and day 5. It was a concern that it seems like this experiment is going to fail. Because if it's increasing, it means it may constantly increase. But to my interest, when we go to day 6 and day 7, the water absorption was starting to get low. So this actually means that a geopolymer can take a certain amount of water. Once it's pregnant with that water, it cannot take any more water in. Then it will just start expelling the water that it has inside it. Then that means that material can be very much suitable rather than our houses. If your house has been plastered with that smooth surface and not painted, and it rains, you'd actually see the water level there marked going through your house. And another thing, that water mark will remain there for like 4 or 5 days. And if there's good sun, in fact. But if there's no good sun, you can actually see that after even 15 days. And at some point, that water mark will still remain there as a marker, as a permanent marker that water was at that stage. Now, if that depends on an ordinary Portland cement, that means at some point, if you build with a Portland with a PPC, this is not a fact. This was just an assumption. if you actually build with it and it rains constantly for 42 days, your house would just melt. Actually, will just melt because the water in there is just too much for the cement to hold. As opposed to this one. This one, a geopolymer, when it actually in certain days, like day 6 there, it actually, day 5, it started expelling the water. It just started taking out water. So that means it has good mechanical properties. It has good geotechnical properties for you to construct with. So geopolymers, now, after this range of experiment that I just did with you guys, now we can conclude that geopolymers are actually good construction materials. Now, if we're saying they are good construction materials, now let's bridge the gap of green matter. Why do we refer as geopolymer cement or any geopolymer material as a green matter? Number one, it's because of the fact that creating a geopolymer does not produce any pollution to the environment. So basically what is happening is geopolymers are taking waste that is there in the environment already and create it into a more sustainable material that we can actually use for building. That's number one. So we can use it as a green matter. And an advantage of it using as a green matter is when it comes to immobilization of elements. Siamo would understand this more since her research is on sequestration. So basically what happens with immobilization of elements is, let me explain it through this picture. So you have seen all the elements that were there, your zinc, your lead, your cadmium that were there on the tailings material. Now, all those materials, all those elements that are there are now covalently bonded here in a geopolymer to form one strength and to make sure that the elements are also covalently bonded. And which means when they are covalently bonded, it's not going to be easy for you to break them out there. So which means those elements now are not going to pose any threat to the environment because they've been immobilized. They're actually covalently bonded, so they're just going to be there. So even if when it rains, those elements or those toxic elements are not going to be washed out of your house and they ended up going to the environment or ended up going to your garden and you started eating your spinach that is lead poisoned. Because they're actually being immobilized, they're actually being formed in a covalent bond. So this is the new world that we need shifting into creating green matters. And also this bridges a gap between green matter and climate change. If we really need to make sure that we live life to the fullest and out of the pollution areas, we need to actually consider techniques such as this one, which is geopolymers. And that in turn, it means then we can actually close all PPC, not PPC, all cements mining that are already there. Then we have eliminated acid mine drainage, we have eliminated air pollution from them, we have actually eliminated the land degradation, and in turn, we've actually created more space for everyone to live in. And on that note, thank you very much, guys. If you have any asks, feel free to ask. I'm gonna stop sharing my screen now.
Thank you so much, Letendou, for that very informative talk on geopolymerization. With that, I will start off the questions section by asking you something that's related to the tailing materials. I want to know what happens to the metals that are on those tailing materials.
Okay, thank you. That's actually an interesting question. And that's what I was trying to actually explain towards the end with a geopolymer covalently bonded. Now, immobilization of metals basically means that now those, okay, immobilization is the opposite of mobile. So the covalently bonding of those metals makes them, it makes them immobile. So now they cannot move, they cannot shift away. Chemists can actually explain this better when they are covalently bonded and when they are strong and tight, that you cannot break them, you cannot actually take those elements cannot move even if any external forces come through. So they're actually covalently bonded, also them within that geopolymer material, and they cannot actually move. I don't know if I answered your question well.
Yes, you actually did. So basically, yeah, thank you for that. The next question, anybody? I see Ismat has a question.
I have a question and a comment. So I first would like to say it's very impressive what geopolymerization can geopolymerization can be used to reduce waste and pollution. And then my comment is, has geopolymerization already been used to construct buildings in South Africa?
Okay.
I have a question.
Padma, can Letendou answer Ismat's question and then we can get back to you?
Okay.
Okay. Yes. It has only been used once. There's actually a video of it on YouTube. I think it was used by this company. I forgot its name, but they were building a Nashua building. The Nashua building that is in, I think it's in Sandton. I don't know. They use it. They use geopolymers in South Africa. That has been once, and they were actually making a slab, but they were doing it in an aggregate format. So in a concrete format. So they actually made geopolymers, sand, water, and concrete to actually create that slab. I'll try to send you a link on that. It has been used in South Africa.
Okay, thank you.
That's very interesting. Padma, I'm returning to you. You had a question?
Yeah, my question is there any disadvantage for the green cement?
Is there any disadvantage? Everything
Yes.
has a disadvantage. And
Yeah.
so, okay, just to add another thing, you know the three, what do we call them? The pyramids of Egypt
Yeah.
that have been dated for a very long time. The reason why they have been standing even today is because they were built from geopolymers. There are actually some evidence that says that those pyramids have been standing today because of geopolymers. You can actually see a documentary of it on YouTube. It's there, that one. So yes, there are disadvantages of geopolymers. And number one being not necessarily on the geopolymer itself, but on the process of creating a geopolymer. Number one, being the fact that it's really not, in as much as we would try to push this, it's really not ideal to have a land that is about 1 hectare. That is just an oven, just to make sure that we elevate that temperature of ambient. It's really a bit thorny of occupying that much of a space. And number two, the vast amount of sodium hydroxide solutions of alkaline solutions that would have to be created. I think for how much material did I think for about 5 kilometer grams, I used over 10 liters of sodium hydroxide. Sodium hydroxide. So you can actually look at that scale. That means now we're not gonna have a lot of, and creating sodium hydroxide also comes with its own packs and its own pollutions as well. So that's, but on the geopolymer itself, there has not been, this is one material that has been battered nicely. It does not have any disadvantage as of yet. It has not been discovered with any disadvantage.
Thank you.
I'm happy, Padma, you were being able to answer. Trevor has a question.
Thank you for the talk. Like, it was really amazing. My question is, if we mix during the process of geopolymer, like I saw on one of the slides that mostly they mix with alkalinity pH of water. So my question is, if we use maybe water that have pH of around 5 or 4, it will be the problem there.
Quite interesting. Thank you. I've actually never thought of that, but now that you asked, it's interesting. But look, it will defeat the purpose of using a sodium hydroxide solution. If we use a sodium hydroxide solution and we still add an acid, then that brings us to a base. then that material is not going to react. So we cannot really use acids. And geopolymers, we don't use water. The only water that we are going to use is actually warm water to actually dissolve the sodium hydroxides, because we actually find them in pellets, in those like tablets. They are found in circular things. I've not seen the powdered one. The one that I've seen is the one that comes in that big container in the lab. So we wouldn't use acid because it actually won't react. Because the idea is to react aluminum silicate material, because they react with alkaline solutions. Because if we add an acid now, the problem is now we're going to be creating an AMD, acid mine drainage. Because what happens with tailings, water, they form acid, then they start becoming pollution.
Oh, okay. Thank you.
Sure.
Helen?
My question is almost like a combination of Ismat and Padma's question. The first part was, if it's so advantageous, why is there only one building? But my main question was, before you answered their questions, was how mainstream is it? Like how frequently is it being used? But now my question is, why isn't it frequently being used?
I think one straight answer is because it's expensive to produce a geopolymer. I think that's one of the disadvantages of it. It's expensive. Expensive on a sense that it's a new technology. The infrastructures are not there set up already to actually produce a geopolymer. Hence, what we have seen so far, it's small scale, created on a lab. And mostly they will be doing it for experimental purposes. And the one building was done because that company is actually not from South Africa. They just operate in South Africa. I think they actually managed to do it nicely because they have resources. So that's part of the reason why it's not used yet nationwide. It's because we don't have the money and we don't have the resources to actually produce it. As opposed to PPC, already the infrastructure are there, the mining are there. We just go in the mine, we mine it, we get it underneath us. The calcite is there, the calcrete is there. So I think that's part of the reason why it has not been used widely. But Egypt has used it to build 3 triangles, and they are still strong even today. But that was back then.
I hope your question was answered. Kiboni?
Besides the fact that it reduces pollution and stuff, do geopolymers have any negative impact on the environment?
In the environment, I don't think so. There have not been any scientific proof that it does. And once that comes to light, then yes, it would be. But up to yet, there has not been any scientific proof that it has harmed any environment. And also looking at the process of a geopolymer, the reactions and all that, we have not had any proof of that.
I hope that that would answer your question. Neschita?
Yes, I don't have any questions because my friends already asked the questions, then I got it cleared. And thank you for the good presentation. And it was all about the new topic, what I learned today, exactly the new topic. So thank you for everything, what you gave to us today. Thank you.
Thank you, Neschita. I actually have another question. My question is... my apologies. Oh, is it okay? Okay. As you mentioned that I do a little work in terms of sequestration and so on. So in part of carbon capture and sequestration, there is now there's another term that and that's not related to me. It's the utilization part of carbon capture and sequestration. So my question is, when we use these tailings, because some of them have been used in terms of carbon capture and storage. So I want to find out then why is it that or how can South Africa get to this point where we use the tailings for CCUS to produce environmentally benign materials which can be used for mine reclamation. Because you also did mention that there's a lot of mines that are not used in South Africa. So why isn't South Africa using this opportunity? Because one, it will make sure that the mines are restored, and two, it will make sure that we are actually assisting in reducing our emissions.
Geologist, I understand your question. I'm not sure if everyone else did understood your question. Too deep, too much of jargons. But okay, part of the reason, I mean, look at sequestration as itself. No? It's not yet even a popular concept in South Africa. It's not yet a popular concept in South Africa. And South Africa, we have a lot of leach hits going on. So that should have been the major investigation now at this point of how can we use sequestration to actually manage these materials and all that and all that. But South Africa, number one, South Africans were too lazy to study. I'm sorry to say this. South Africans were too lazy to study. You got your honors, you're done. You go to work, you're done there. We don't actually elevate ourselves to go to research. And even after we have studied, we want to work into technical environments. We don't want to work into research infrastructures. And if we were working there, I'm sure we would have come with a lot of solutions. Number two, resources. Money allocated to research. It's quite low. Imagine you have to finish your PhD with 120,000. How can you actually conduct a fully nice, worldwide known study with 120,000 rands? You know, I mean, isn't it what NRF gives you for PhD? Okay, I actually forgot. I think it's that, because for masters I know it's 80K. So how do you actually? I mean, in honors they give you 60,000, and they want you to actually come with a study with 60,000. There are fees. There's a rest already. They've charged 30,000. Now, how are you going to run your fees in your research? Helen was crying earlier that the next 3 months she does not know how she's going to fund her project. You see, so that's one of the things that South Africa will lack on: funding, allocation of funds into research and development. But one of the only issues that we always hide on, corruption. I think corruption has actually messed everything up. They are looting in the Department of Education, and the very funds that are allocated to actually promote education, they're actually going into the pockets of comrades. So that's part of the reason why South Africa were a bit behind. At some point, I tried applying for masters in Michigan University. And while I was going through the application, they told me that I actually saw that all PhD students, they are funded, fully funded. Immediately you register for a PhD, you have a funding from the university. But in South Africa, there's someone who's doing a PhD who does not even have the even NRF, you know. And that's part of what is contributing to us not actually having such infrastructures. And if we had researched a lot, we'd actually come up with a good solution. And actually, it's actually good. There are some structures such as Access, HPW, that CSIR, you know, those are research centers that are actually trying to actually push for that. But that's the one center that we have in South Africa. CSIR is the one that is also pushing the ventilators for coronavirus. You know, imagine if you have like 9 structures in 9 provinces. Each province has its own structure, which is not CSIR, not CSIR having 9 branches, just different ones. You know, would actually have been more grown and all that. So I think that's one of the things that it's really wrecking our education system in South Africa. And sadly, there's nothing we can do about it.
No, I hear you. I hear you. Hopefully in the near future, you can get to a position where you can ensure that young students for the future have those abilities and resources to make sure that, one, they can further their education, and two, that they can actually focus on research-based things. Yes, Letendou?
Yes, South Africa has just passed a new law that an independent person can campaign for president. So if you vote for me for president, when I campaign as an independent, Amanda, education is going forward.
Letendou for president.
You have my vote.
Thank you.
I'm going to take it back to Carl.
No, as I said, I've been answered. Thank you, Tiamo.
Okay. Is there anybody else that wants to ask our key lecturer anything? If you want to, just switch on your mic and speak freely. Okay, I guess everybody was so excited and so mind-filled with everything that you said, that you have answered all the questions and you have filled all the gaps that they had. And with that, I just want to thank you, everybody that tuned in from YouTube. And I also want to thank you again, Letendou, for taking time out to come and educate us. And with that, thank you so much, and enjoy the rest of your day and stay safe.
Thanks, everybody. Maybe just a big round of applause for our speaker today before I take off.